This is the cell at resting potential of negative 70 millivolts. Despite having positive potassium ions inside the cell, it is negative from the proteins and nucleic acids. In the outside environment, it is positive from the positive sodium ions. Although there are negative chlorine ions outside and inside the cell, they do not have much of an impact at this moment. During this time, the sodium-potassium pump, or NAK+ pump, is working to keep the cell at resting potential and is constantly taking out 3 sodium ions and putting in 2 potassium ions. The first phase of an action potential is depolarization. Depolarization occurs when a ligand or neurotransmitter binds to a ligand-gated sodium channel. This binding of the ligand causes the channel to open and allows the inflow of sodium into the cell. This increases the membrane potential. As the membrane potential rises, more sodium-gated channels will open along the membrane because they're voltage-gated channels, and open once the membrane potential hits a certain voltage. Once the membrane potential reaches negative 55 millivolts, the response will be sent, and most of the sodium channels will open because the sending of an action potential is an all-or-nothing event, and negative 55 is the threshold. Eventually, the membrane potential will hit positive 30 millivolts. This therefore depolarizes the cell and reverses the charges, making the inside of the cell positive and outside negative. The outside of the cell being negative is partly due to the chlorine ions, for they have a big part during depolarization. After reaching positive 30 millivolts, the voltage-gated sodium channels will close. During this time, the sodium-potassium pump is constantly using ATP and putting 2 potassium ions into the cell and sending out 3 sodium ions. The next step in an action potential is repolarization. Once the membrane potential hits positive 30 millivolts, it triggers the sodium channels to close and the potassium channels to open. The potassium ions will therefore flow down their concentration gradient and out of the cell. This causes the inside of the cell to return back to being negative and the outside of the cell to be positive. This outflow of potassium ions decreases the membrane potential. As the membrane potential gets lower and lower, more potassium-gated channels will open, allowing for the outflow of potassium to increase. This occurs because the potassium-gated channels are also voltage-gated channels and open when the membrane potential is at a specific voltage. Because the potassium channels take time to close, the membrane potential will actually reach negative 80 millivolts and below the actual resting potential. This step is called hyperpolarization. By going down to negative 80 millivolts, it ensures that the signal will be passed along down the axon and will not go backwards or up the axon. Around the second half of repolarization and all throughout hyperpolarization, the inside of the cell is negative and the outside of the cell is positive. Once the potassium channels fully close, the sodium-potassium pump will use ATP and move into potassium and out sodium, and will therefore basically become the main functioning channel to return the membrane potential to resting potential of negative 70 millivolts.